Hello, so in today's video, we're going to look at this iteration in this form here. So consider an iteration an plus 1 is equal to r times the previous number in the sequence an, and then plus a constant c, where c is a real number. So this is kind of like a geometric sequence, but you've just got this plus c at the end. So this plus c there could be, well, it could be 0, could be 1, could be 2, could be negative numbers, any real number you like. So it's kind of a geometric series, but yeah, a geometric sequence up to a constant because of this constant up there. So consider this essentially, I'll call it a pseudo geometric sequence where a0, the first term is a, and the common ratio is less than 1. So if your common ratio is less than 1, this is going to be a convergent sequence. So for example here, this could be an example. Let's consider an iteration an plus 1 equals 0.5 an plus 10 with the first term 1. So the sequence goes 1, 10.5, 15.25, and then you plug that into this point there, into this this value there, half 15.25, and then add 10 to it to get your next number, and so on and so on and so on. So consider that iteration. What is the limit of this sequence? So eventually the sequence is going to converge and converge and converge as it goes on and on. But what would be the limit of a sequence like this? How could you get a formula for the limit of a geometric a pseudo geometric sequence? I call it a pseudo geometric sequence. Let me just do this here. So a pseudo geometric sequence. How would you find the limit of something like this? So let's look on the next page. So we've got, again, this iteration, this iterative formula, an plus 1 equals r. The ratio, again, I'll just make it clear that the modulus must be less than 1 in order for the sequence to be convergent. So r times an plus c. So the first term in the sequence is going to be r times a plus c, because our second term, so our very first term is a. So plug that into the formula, a times r times a plus c. That's going to be our next term in the sequence. So our next term in the sequence is going to be a2, which is r times by our previous number, ra plus c, and then plus c at the end. I'm just going to actually expand the brackets here, so we get r squared a plus rc plus c. And then that's going to give me r squared a. And then I'm just going to factorize the c. And if I do that, I get c times by 1 plus r. So just factorizing the c times 1 gives me the c there, and c times r gives me the rc there. So I'm just going to write it like this, and you'll see why I'm doing this in a minute. So then our next term is going to be a3, and that's going to be r times by our previous term in the sequence. So r squared a plus c times 1 plus r, all in brackets, and then plus c at the end. Again, I'm going to expand this. So we get r squared a plus rc times by 1 plus r, and then plus an extra c at the end there. So again, I'm going to factorize out a c again. Well, I'm just going to expand out. I'm just going to expand the brackets actually first. So we get r squared, sorry, r cubed. This is incorrect here, sorry. R cubed here. So you get r cubed times a there, and then expanding these brackets, we get rc plus r squared c plus c. Again, I'm just going to factorize a c out from the brackets there. So from these like three sums here, so c times 1 plus r squared. So if we keep on continuing this sequence of iterations forever, I'm not going to do the next one, but if you were to do the next one, a4, you should get r to the power 4 times a plus c times 1 plus r squared plus r cubed. So basically, the way this works is that your r, the power of your r there is the same as the term, the number there, and you sum these terms 1, r squared, r cubed, all the way up to the number there, take away 1. So basically that means that your value of, let's just say ak, your k plus 1 number in the sequence, because a0 is your first number, so a1 is your second, a2 is your third, so ak is going to be your k plus 1 number in the sequence. So that's going to be r to the power of k times by a plus c times by 1 plus r squared plus r cubed, all the way up to r to the power of, I just put a dot 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 here, dot dot dot, r to the power of k minus 1. Okay, so then let's think about this. So if k is a very massive number, what's going to happen to this result? Well, if k is huge, remember that r has a modulus less than 1. So this is a number here, this r, which is a size less than 1. Now do something like 0.5 to the power of a massive number in your calculator, or even something like minus 0.5 to the power of a massive number in your calculator. This is going to go to 0 because a decimal between 0 and 1 to the power of a massive number is essentially close to 0. So this is going to go to 0 as k goes to infinity. So as k becomes massive, r to the power of that number will be 0, pretty much 0. 0 times any number is just 0 there. This a there is just a whole, not a constant value. So this is going to go to 0 as k goes to infinity. So what we've got then is we've got the limit of n. Let's do like we said back here, the limit as n goes to infinity of an. So the limit as n goes to infinity of an, sorry, is going to be this limit as n goes to infinity of our result here. So this r to the power of n times by a plus c times by 1 plus r squared, all the way up to r to the power of n minus 1. Now, okay, so again, the first part here is going to tend to 0. So this will go to 0. It's going to tend to 0. So we're going to be left with the limit as n goes to infinity of this c times by 1 plus r squared plus plus r to the power of n minus 1. So this is now, so as n goes to infinity, this number there goes to infinity. This is going to become an infinite series. Now, what you'll probably notice, hopefully, is that this series, this sum that we're doing, sorry, let me just make the writing smaller. So I'll try that again. No, let me move my mouse down here and try that again. Right, so as n goes to infinity, we've got now an infinite series. So this here is an infinite sum. So we've got basically, this is just a constant c. I'm going to bring to the c to the front of the limit because it doesn't matter where the c is. It's just a constant. So the c could go there or it could go there. Doesn't matter where the c goes. So we've got c times the limit as n goes to infinity of this sum here. But this is actually an infinite sum. So because n is going to infinity. So really what this is going to be equal to is it's going to be equal to the sum from n equals 1 up to infinity of this sequence of numbers here. So r to the power of n minus 1. Sorry, let me change the letter here to a k instead. So k there, r to the power of k minus 1. Okay, so we're starting from k equals 1. When k equals 1, we've got obviously k equals 1 there. 1 take away 1 is 0. R to the power of 0 is 1. So that's where the first term comes from. And then when k is 2, the second term is going to be r to the power of 2 minus 1, which is r to the power 1. That's where that term comes from. So that's why this formula works. So we're doing this summation there to infinity. Now, this is a geometric series. So why is this a geometric series? Because we've got 1 r squared, r cubed, and so on and so on and so on. This is a geometric series because we're multiplying by r each time to get our next number in the sequence. So the sum here is a geometric series, and it's an infinite geometric series, and it's a convergent geometric series because remember, we've got r must be less than have a modulus less than 1. So this is a convergent series. So convergent series. So we can use our convergent series formula that we used in the previous lecture. And that was this formula here. So the sum to infinity for a convergent geometric series was, I'll just write convergent geometric series here. So for a convergent geometric series, our formula goes the first number in the sequence divided by 1 minus the common ratio. So if we look at this sequence of numbers 1r, r squared, r cubed, the ratio is r, the common ratio is literally r, and the first term in the sequence is 1, so a equals 1 is our first term. So we've got c, so this is going to be equal to down here, c times by the infinite sum of our geometric series, a first term of 1 divided by 1 minus the common ratio, which in this geometric series is r, so 1 minus r. So we get a final result of c over 1 minus r, and that's our final result. So when you've got an iteration like this, a sequence like this, what I called a pseudo geometric series, the limit of that sequence, the sequence is going to tend to c, so this number at the end, divided by 1 minus this ratio there. So that's how you can work out the what your sequence tends to. So let's look at an example. So let's look at a sequence here. We've got an iteration an plus 1 equals a quarter times an minus 5, where a0 is 10. What is the limit of this sequence? So as n goes to infinity, you keep on iterating this formula again and again and again. What will this sequence tend to? So we're just going to use our formula. So limit as n goes to infinity of a pseudo quote geometric series. That's going to be the c value divided by 1 minus r, as our formula says back down here. So our c value is the number at the end, the constant. So the c value in this case is minus 5. And the r value, our ratio here, is a quarter. So we want to plug those numbers into our formula. So we get minus 5 over 1 minus a quarter. So that's going to give us minus 5 divided by 3 over 4. And that's going to give us minus 5 times by 4 over 3. So minus 5 times 4 over 3, which will give us minus 20 over 3. So the result for this is going to be minus 20 over 3. So the sequence, if you keep on iterating the sequence, you're eventually going to tend to minus 20 over 3. So again, the key result is that if you have an iteration, an plus 1 equals a ratio times by the previous number of the sequence plus c, with the first term. So actually, yeah, this limit is independent of the first term. So the first term in the sequence really doesn't matter what it is. Your limit as n goes to infinity, the limit of your sequence of this convergent sequence where your ratio is less than 1 is always going to be the c value divided by 1 minus r. And that is the formula you can use to work out limits of these kind of semi convergent geometric series.